Hey, hi guys, good morning. So sorry for the delay. I was taking a demo. All right. Okay, so any questions, guys, before we get into the session? Any questions? So yesterday it was a long session, so whatever we discussed, it everything understood, or do you have any questions anywhere?
So Shrikant, I mean, we need some, case scenarios, how in, certain case scenarios, what we have to, which formula we have to apply where, based on
Okay, so
what statement.
yeah, we
Yeah,
have
we need,
gone through some of the examples yesterday. If you need more, then we will plan for more examples. So today
yeah,
also,
like, yeah,
yeah.
like what a data scientist, what kind of statement, what problem description he'll be given. So where he'll use which formula to get what information.
Okay, okay, I got that point. So see now for after every topic, what I'm covering is certain examples which will give you an which will give you an understanding that where that particular concept can be used. Okay, so I will again, cover those things so that you will understand. But but after a while, when we cover other topics also, now you will be having a good understanding about a lot of different concepts. And for every concept, I will give you small examples. But sometimes in the real scenario, what will happen is one particular solution may not be enough. Okay. So if you look at that particular problem statement, probably you may have to use multiple concepts. Okay. So those kind of scenarios, I will take it later because at that time you will understand, better. But currently we are taking a baby steps where we are covering one small topic and then we are taking one small example and seeing that, okay, how that particular concept can be applied there. But when you get into a real scenario, the problem could be much more bigger. And for that, you may have to use multiple different techniques, to solve that problem. Probably you may have to develop a classification model. Along with that, you may have to do some kind of an inferential analytics and some kind of a correlation analysis. And in that way, it would look as a complete solution. Okay. So now, whatever topics we are covering, if you have any confusion there, if you want more examples there, do let me know. But the bigger picture, you will get it in the end only. Okay. Once you understand other concepts as well. Okay.
Okay, thanks. Yeah.
Yeah. So, okay. So let me. Okay, so yesterday class we talked about distributions. Okay, so we understand that the distributions, these probability distributions, are the distributions which we can use, to calculate the probabilities of certain scenarios to happen. Okay, and even to generate certain scenarios, we can use this distribution and we can do some kind of a simulation to generate different scenarios. Okay, which we can use it for our analysis. So two ways we use this distribution. One way is, to calculate the probabilities, and second is, to generate the data. So why we generate data? So in some cases, we don't have all the scenarios available. So in those kind of scenarios, if we have some understanding about the variables, about their distributions, then we use this distribution to generate the data and to generate those kind of scenarios on which we can do some kind of analysis. So that's one. So now, where to use which distribution is the next big uh, question. Okay. So for firstly, there is a high level categorization. If the variable is categorical variable, then we can use these discrete distributions. If the variable is a continuous variable, then we can use these continuous distributions. Now, again, in the categorical distributions, we need to decide whether we have to go with binomial, Poisson, or hypergeometric. So yesterday we discussed about each of these distributions. So binomial is all about it's all about where you have only two outcomes for any trial, okay, either success or failure. Okay, in those kind of scenarios, if you want to understand after n number of trials, what would be the chance of getting uh, a particular number of successes, okay, or particular number of failures. If you have that kind of a problem, then you can go with a binomial distribution. Then we have seen that, okay, what what formula we can use, to calculate the probabilities of those scenarios. So we have taken this example. Again, I'm repeating. So if you do not understand, please let me know. This is one of the scenario where we were, sorry, not this one. Yeah, this was the scenario what we have taken, where I just wanted to find out what would be the probability that three customers who are coming into my store, out of those three, two will purchase my product. So that's the kind of probability I wanted to calculate. And here I know that, okay, for every trial, a customer coming to my store, either he will buy or he will not buy. So it is a binomial, okay, kind of decision or binomial output, either 0 or 1. So I need to understand whether a particular trial has a binary outcome, okay, 1 or 0. And based on that, I have to translate that problem statement into a analytical problem and decide whether this binomial distribution would fit to that particular problem or not. So here my problem is to calculate the probability that exactly two customers will purchase out of three. Okay. So the traditional way is like I can go and construct the tree like this, and I can, based on this, I have to calculate the probability. So here the chance of purchasing is not, and chance of purchasing and not purchasing is not equal. So chance of purchasing is only 30% and chance of not purchasing is 70%. So here, if I have to calculate the probability, it is not that straightforward. So that's the reason, I will go and refer to this binomial distribution. And this binomial distribution can help me, to calculate those probabilities quickly. Either you can refer to the binomial distribution table, or else you can go ahead with this particular formula where you require three parameters, which is probability of success, the number of trials, and number of successes which you would like to calculate. So X, N, and P. So if you have these parameters available, then you can just use this formula to calculate the probability. Okay. So is this particular part is clear, or you need any more examples? Agway, you have asked this question, right? So is this part is clear?
Yeah, it's clear here.
Okay. So binomial distribution, I'm considering it is clear to you guys. Now, after that, we discuss about Poisson distribution. Again, see, Poisson distribution, the output is a discrete number. Okay, it's a countable number. So it's about finding out how many occurrence may happen, in a particular interval. Okay, so per thousand feet or per square foot. So this is the range in which, I want to calculate the number of occurrence of the events. Okay, so if you have these kind of scenarios which you need to analyze, then you can go with a Poisson distribution. So here we have taken this example. So for example, if I want to analyze, or if I want to calculate the probability of certain number of events to occur in a particular duration of time or period, then I can use this Poisson distribution. So for example, I have some high level idea that there could be 3 or 4 customers per 4 minutes who will enter into my store. And now I want to predict that what is the probability that 10 customers per 8 minutes, okay, would enter my store. Okay, it is little bit of hypothetical. Nobody measure per 4 minutes, per 8 minutes. You can consider it as per 1 hour or per 2 hours, okay, or per 5 minutes or 10 minutes. Okay, so you can change the scenario. So let's suppose if you have a problem like this where you want to measure the rate of event events occurrence. Okay, so you want to measure the probability of the rate of uh, occurrence of the events, there you have to go and use this Poisson distribution. So we have seen what is the formula for probability calculation for this Poisson distribution. You have to substitute the values and you can calculate the probability. So that is on Poisson. So here this x can take any value, and these values, any value means it can take any discrete value. It cannot take decimal values. And that's the reason it falls under discrete distributions. Here in the binomial distribution also, there also the numbers are discrete. X can take, for in this example, here X can take either 0, 1, 2, and 3. Okay, so it can't take 0.5, 0.8, or 1.2, 1.3. Okay, so that's the reason it is also considered as a discrete distribution. And after that, we have talked about hypergeometric distribution. It is a very specific scenario where there would be a finite population, and from that population only we are drawing the samples. So here, when we are drawing the samples, here the samples will be drawn without replacement. So here it would be different than a binomial distribution. Here, the formula would change when we talk about probability. Here, we require a population size and the number of successes in the population, the sample size, and the number of successes in the sample. For that, we have discussed about this particular example where we have to find out the probability that 2 out of the 3 selected computers have some illegal software loaded. Okay. So there, for that, we also need the population details also. What is the overall population? And in overall population, what is the number of computers which have illegal software loaded? And then when we are drawing the sample, we are checking what could be the probability that when I draw a sample size of 3, in that, 2 will be illegal. So for that, we are going with a hypergeometric distribution. Then we talked about continuous. Here the variables, here the values can be continuous. It can be of decimal values. So for example, thickness, time, temperature, height. Okay. Here we talked about 3 different distribution: uniform, normal, and exponential. So uniform distribution says that, okay, the probability of every value between the range will have an equal chance or equal probability, and that probability is nothing but 1 minus range. Okay, the uh, the maximum minus minimum value. Okay, so here we have taken this example, the flight time. Okay, and when we are talking about continuous distribution, here we can find here the probabilities will be calculated for a particular range. Because see, in the continuous variable, we don't calculate the probability of exactly of a particular value. We will not say that, okay, what is the probability that a flight would take 120.22 minutes? Okay, we will generally that will not make sense. So in the continuous variable, definitely every time we'll talk about a range. What is the probability that the flight may take time somewhere between 120 minutes to 130 minutes? So that would make sense. Exact value we never consider when it considered to continuous variable. Okay, when we are talking about probability. So here we'll talk about the area covered in that particular range. So if my interest is to find out the probability that this flight time would be somewhere 120 minutes to 130 minutes. So here in this particular distribution, I will try to capture this particular area, and that area will give me the probability of getting that value between 120 to 130. Okay, so after that we talked about exponential. Exponential is just opposite to your Poisson distribution. So it's about the time taken between the two occurrences. There we are talking about in a particular time how many number of occurrences in Poisson. In exponential, it's about how much time it will take between the two occurrences of the events. Okay. So time arrival between the vehicle, time between the vehicle arrivals, time required to complete a questionnaire, time distance between the major defects. These are some of the scenarios which you can relate to this exponential probability distribution. Okay. Here, what example we have taken? Here we have taken this particular example where we are calculating the probability of two successive arrivals, okay, which will take 2 minutes or less. So here we are. So here the time could be, it can take any decimal value. Okay, it could be 2 minutes or 2.2 minutes or 1.8 minutes, 1.9 minutes. Okay, and my interest is on this particular range. Okay, here I want to find out the probability that the time taken between the two arrivals of cars would be 2 minutes or less. So I need to calculate this probability, this region. So that we can calculate through this particular formula of this exponential distribution. So what we discussed is that you don't need to by heart all this formula. Okay, in Python everything can be done much more easier. So let's jump to this Python. Okay, so here we will take this particular package for all these distributions. Okay, so in SciPy, which is a scientific computation package, in that we have this stats module, statistics module. In that, we will have different distributions. So we will pick up different distributions, and then accordingly, we will use it, for our calculations. Okay, so here I'm picking up first binomial, scipy.stats import binomial. And this is the formula just for your understanding, for your reference. I've also provided you the formula. Okay. Uh, 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 okay. So I'll come back on this. Let's go to this particular portion. Okay. So binom is the function which you can use it for binom. So here we have in this binom function, again, we have two different methods. One is PMF, which is probability mass function. And then we have CDF, which is known as cumulative density function. Okay, so what it does. So in binomial distribution, you know that we require three parameters. Okay, one is the number of trials. Second is the number of successes, which we need to, on which, we want to find out the probability and the probability of success. So for example, this is the example. I'm taking a different example now. For example, Nathan makes 60% of his free flow attempts. So it says that, okay, there is a 60% success, okay, what he's getting for every free flow attempts. If he shoots 12 free throws, what is the probability that he makes exactly 10? Okay, so that means he will get 10 successes. So the total trials is 12. The number of successes on which I need to find out the probability is 10. Okay, and P is probability of success is 0.6, which is 60%. So here I'm saying exactly 10. So that means I want to find out the probability of X equal to 10. Okay, given that the P is equal to 0.6 and the number of trials equal to 12. So I'm taking this binom function, in that I'm taking this probability mass function. This PMF gives the probability of exactly the value at which, I want to find out the probability. So I'm saying I just need to pass this. I'll run this. So I'm getting an error. So why that error is because I haven't loaded these packages. Okay, so let me load this package. So when you will get these kind of errors, the name error, so what it means is name binom is not defined. So that means this particular Python program is not identifying what this binom is. Okay, what is this name all about? So until unless you do not install and load that package, it will not understand what this particular function is all about. So now when I ran, so now I'm not getting that error and it is giving me this value. It's saying 0.063. So that means the probability is only 6% that he will make exactly 10. Okay. Now take another scenario. So Marty flips a fair coin 5 times. Fair coin, you have to keep it in mind. 5 times, what is the probability that a coin lands on heads 2 times or fewer? So see, now you have to understand this problem now. Here I want to find out the probability of getting 2 times heads or fewer. So that means I want to find out x equal to 2 plus probability of x equal to 1 plus probability of x equal to 0. 2 or 0. So 2, 1, 0. Okay. So I want to find out the probability of all these three, and then I want to take a cumulative sum of all those things. Either you can take this PMF and you can run it 3 times by putting k equal to 2, k equal to 1, and k equal to 0, and then add all those probabilities together. Or else you can do it once, by using this CDF function. If you say CDF, automatically it will, in the backend, it will calculate the probabilities of 2 or less than 2, and then it will give you the cumulative sum of that. Here, the number of times trials is given 5 times, but probability is not given. So, but it says that it's a fair coin. So, fair coin means it has a 50% chance of getting heads and 50% chance of getting tails. So, here the P would be 0.5. If you run this, it is giving me the cumulative sum. Now, let's do a quick check on this. So, I'm taking this PMF. So, now I will pass all these values. So yeah, k equal to 2. So now it is giving me 0.3. So 0.3 means the probability of getting exactly 2 heads. Okay. Now I will take it for 1 is 0.15. Now I'll take it for 0. Now it is 0.03. So combination should be, the total cumulative should be 0.5. So now let me do it in one single step. I'll say plus. I'll say k equal to 1, k equal to 2. So it is saying 0.4999, which is nothing but 0.5. So either you can do it in this way, or else you can directly use this binom.cdf and you can calculate this at once. Okay. Now, this is another example. It is known that 70% of the individuals support a certain law. If 10 individuals are randomly selected, what is the probability that between 4 and 6 of them support the law? So now here I'm talking about the range. It is not at at most kind of a problem. It is saying that somewhere between 4 and 6. So now what I have to do is I'm taking this CDF function. I'm saying k equal to 6. So if I'm taking CDF, k equal to 6 means it is calculating the probability of 6 or less than 6. Okay, till 0. So from 0 till 6, okay, this function is giving me the probability, right? But I'm interested from 4 to 6. So that means less than 4, I'm not interested. Okay, so 3, 2, 1, 0, I'm not interested. So what I'm doing, I'm calculating another CDF, okay, for k equal to 3, 2, 1, and 0, and subtracting from this particular CDF. So I will get this particular probability of this range from 4 to 6. I hope you got it right. So this is how I can use this CDF function, to calculate the probabilities of whatever range of values I want. Okay. Now, if you want to generate the values from this binomial distribution, then you have to use a NumPy package. Okay. So SciPy is more about for calculating the probabilities. If you have to generate the values, then you have to use this NumPy package. In that, you go and import this random. So random generation. If you want to randomly generate certain values, okay, then you have to mention from which distribution you want to generate those random values. Okay, if you will see that, okay, in some of the use cases we will generate certain samples. Okay, and if we use just random, by default it will take the normal distribution. But if you want to specifically generate the values from particular distribution, then you have to specify that distribution. So for example, here in the random, I'm using for generating samples, and for generating those samples, I'm using this particular distribution binomial. And again, you have to give the properties and the characteristics of those distribution. Yes, it is binomial, but that binomial distribution what characteristic that distribution is having. So then you have to say that this binomial distribution characteristics is that number of trials is equal to 10, probability of success is 0.25, and the size, the number of values which I want to generate is equal to 100, which is sample. So now whatever the values it will generate would be, those values would be between 0 and n, between 0 and 10. And based on the probability of occurrence of each of the values, you will see that many values, the values would be generating based on those probabilities. Okay. So if the probability of 5 is higher, then you will see more 5s getting included in your sample. Okay, so that's how you can use this distribution to generate the values. So that's how I got this particular array of values, 100 values coming out from this binomial distribution. Now I can use it for my analysis. So are you guys following, everyone? Do you have any questions? Now if you want to kind of plot, okay, certain values, okay, this binomial distribution. Let's suppose first I generated this particular, what do you say, list of values, okay, from random.binomial with the particular characteristics of n equal to 10 and p equal to 0.5. And then I created a data frame, okay, of this particular variable. And after that, I kind of, created this plot, okay. Now this plot will give me an indication like, how many points have been generated from for each of those values. So basically it is a frequency and these are the values. Okay, so it will give you some kind of indication like which of the values have higher probability, to be chosen. So for example, here 5, 4, 6, these are the values which has higher chance to be chosen, okay, from this distribution. Okay, now let's move to Poisson. Okay, so few people pronounce it poison, few people pronounce it Poisson. Okay, so the right way is like Poisson, where I is silent. Okay, so here I'm going with this Poisson distribution, where in this Poisson distribution you just require that lambda. Okay, nothing else. Okay, so here I'm generating these values. Okay, either you can use NumPy, and even with this function you have this RVS method through which you can generate values. So I'm just passing this lambda or mu equal to 3. So that means 3 occurrences per interval of time. Okay, size equal to 10, then it has generated the values. Okay, and these are all discrete values. Now here also, let's take this example. A store sells 3 apples per day on average. So here, whenever you see the word per, okay, a rate, then you can blindly go and consider this Poisson distribution. So on a daily basis, 3 apples per day the store sells. Now the problem is, what is the probability that they will sell 5 apples on a given day? On an average, they are selling 3. So there would be a scenario that sometimes they may even sell more than 3 or less than 3, right? So what is the probability that they would sell 5 apples on a given day? I'm taking a very toy example, but you can scale it to whatever level you want. So if, let's suppose, for a manufacturing business, what is the probability that they will sell 5 tons of apples, okay, or apple juices in a given day? Okay, so you can scale it to that level. So I'm taking this Poisson distribution. I'm taking this again PMF. PMF is exactly 5. Exactly 5. Okay. For exactly 5, it is only 10% chance. Okay. Now, if you want to say that at most 5 apples, then you can go with CDF. So for example, in this case, a certain store sells 5 footballs per day on an average. What is the probability that this store sells 4 or less footballs in a given day? Okay. So now you can take this. If you want to find out Now take it an exercise, do it yourself. I want to find out more than 4. How you will find out more than 4? Can anybody tell me? If I want to find out what is the probability that this store sells more than 4 footballs in a given day? 5, 6, 7. How would I calculate?
So we'll get the PMF for 5, 6, 7 and add that.
So why till only 7? There could be more than 7 also, right?
But then it will be
7
infinite.
is the average. So till infinite,
One,
how would I calculate? Yeah,
one
7.
minus.
Yes. I'll just do 1 minus this. That's all. See, if I get the probability of less than 4, and I know that overall sample space, probability of the sample space is equal to 1. So from the total, if I subtract that, and I will get the probability of greater than 4, right? So now for less than 4, it is 0.7. So I'll just take 1 minus, so probability is 0.882. So see, now the probability of selling more than 4 is pretty high. Okay, so then accordingly, I will kind of plan my resources. So there is 82%, 83% chance that, okay, on a daily basis, I may sell more than 4 footballs. Okay, so exactly this is the problem. So a certain store sells 15 cans of tuna per day on average. What is the probability that this store sells more than 20 cans? So all these functions will give you the left hand side of the probability. So so even if you have considered if you refer to that Z table and T table which we have discussed in the previous classes, so all those probabilities were giving me the left hand side of the region, right? So if I want to find out on the right side is greater than certain value, right? Whenever we have to calculate the probability of greater than, then we will first calculate the probability on the left hand side, which is lesser than, and then subtract it from 1, to find out the right hand side of the probability. Okay. So here I've taken first, I'll say Poisson.CD of k equal to 20. So what it will do, it will calculate the probability of k equal to 20 or less than 20, right? And that probability I'll subtract it from 1 to get the probability of k equal to k greater than 20. I hope you guys are following, right? So the way we have done it here, in the same way we are doing it here. Okay. So here the probability is pretty low, okay, for selling more than 20 cans in a given day, which is kind of only 8%. Okay. So with these probabilities, now business can make better decisions. Do you agree or not? So now they can play with this. Okay, they can change the K value and they can find, okay, what is the chance of selling more than 10 or more than 20, more than 30. Okay, and accordingly, they will plan their resources so that they can meet the demand. It is again, just to add on the distribution. Now coming to the uniform distribution. Okay, so here for the uniform distribution, we require the range. Okay, we require the maximum value and the minimum value. That's all we need. Okay. So for example, suppose a bus shows up at a bus stop every 20 minutes. Okay, and if you arrive at the bus stop, what is the probability that the bus will show up in 8 minutes or less? So here we have this range. So range is given, okay, every 20 minutes. So in 20 minutes range, the bus comes. So here we want to find out what is the probability that bus will show up in 8 minutes or less. Okay. So here we have to find out the probability at x equal to 0 and x equal to 8, and we will subtract. So for example, let's take this. So we have to find out the probability of this particular value and this particular value, and we can find out the range of that. So here we are talking about 8 minutes or less. So, okay, so I think in this case, If you say 8 minutes or less, just we'll take this CDF function and just say x equal to 8. Okay, so 0.4. So this LOC means, what is the starting point? Okay, 0. And scale means the range. Okay, from 0 till 20. Okay, that is the range. Okay, what we are talking about. And we are interested for x equal to 8 or less than 8 because we are talking about CDF. It will take, if we consider it as PMF here, sorry. So PMF is not the function of this. For uniform, this PMF is not working. Okay, so I'll come back on that. If you want to find out exactly, so it's simple. Okay, so you just need to say 1 by 20. 1 by 20 is the probability for exactly x equal to 8. So it is the same probability for all, right? So that's the reason probably PMF is not working because the probability will be the same across for all the values in uniform distribution. So if you're using CDF, then we are saying that it's the probability of x equal to 8 or less than 8. Okay. Similarly, if we make it as 9, so the chance is 45%. So like that, you can use this function, to find out the probabilities of a uniform distribution. Let's take an example. Weight of a certain species of frog is uniformly distributed between 15 and 25 grams. So it's a range of the weight of these frogs. If you randomly select a frog, what is the probability that the frog weigh between 17 and 19 grams? Okay, so I'll take the highest one, okay, and find out the left hand side of the probability from 19 till 0, okay. And yeah, here the range is, starting range is 15 and the scale is 10, right? The range is 10, so scale equal to 10. So from 19 till 15, okay, and it will give me the probability from 19 till 15 because 15 is the minimum point, okay. And from there I will subtract, and then I will subtract the CDF function of 17. 17 will also take from 17 till 0. Okay. So with that, I will get a probability of a range between the 19 and 17 only. Okay. So that is giving me as a 20%. So like that, if you want to find out the probability of a particular range, then you can take the highest value first and consider the CDF of that highest value and then subtract the CDF function of the lower value. So that will give you the probability of that particular range. All right, so now normal distribution. And this is the most common distribution for continuous variable. Most of the time we consider the normal distribution only because the name suggested that it is very normal, that any continuous variable will follow this kind of distribution. That's the reason it is called as a normal distribution only. Okay. And for normal distribution, it requires uh, standard deviation and the mean. So these are the two parameters which we require for normal distribution, the mean and the standard deviation. So I'm passing the x for which I want to find out the probability, and I'm passing the mean and standard deviation. Here I'm using CDF because in continuous variable, the CDF only makes sense. We will not find out the probability of an exact number. Okay. So here we go with a, okay, so one second. Yeah, uniform is a continuous variable, right? So here we use PPF. Oh, sorry. Okay. Okay, so I'll check on that uniform distribution. So if we have to find out the the probability of a particular range, then we will go with this CDF function. So here I want to find out the probability of having a number as 68 or less than 68. So I'm passing that number, I'm providing the mean and standard deviation. So it will give me the probability of that particular value, which is 84%. Okay. If I want to find out the probability of a particular range, like between 63 and 68, then I'll take the higher value CDF and then subtract it from the lower value CDF. And subtract the lower value CDF from the higher one. So that is give me the range of the probability between that particular value, 68 and 63. Okay. Now this PPF. PPF is interesting function. So if you know the probability, and based on the probability, if you want to find out the number, okay. So for example, I want to find out at 95% chance, what would be the value, okay, below which, I'll get the values, okay, at 95%. So here, if you see at 0.95, so I'm getting 69. So that means 95% chance is that the values will be uh, either 69 or less than 69. Okay. So if I quickly show you the,
What is PPF? I mean, what is the full
I'm
form
telling
PPF?
I'm telling you. Suppose this is my normal distribution. Okay. So firstly, I want to find out, let's suppose this first problem. Okay. I want to find out what is the probability of getting a number between this particular range, which is 63 and 68. 63 and 68, let's suppose. Okay. So now with this particular CDF function, I got that it is 84%. 84% of the values in this normal distribution falls between this particular range. So the probability of getting any number between 68 and 63 is 84%. So that we are finding out through CDF. Now what PPF is telling me, I want to find out at 95% what would be the higher value at 95%. So it is giving me this particular value, which is this 69.6. So this is 69.6. So as I mentioned, all these probabilities will be on the it will only capture the left hand side of it. So when you're passing this 95%, it will capture the from the left. So it's saying this 95% from the left hand side till 69.6 value, there are 95% of the values which falls in this particular range. Are you getting? So PPF will take the probability and give you the value, while CDF will take the value and gives the probability. So it's just opposite. Okay. Are you getting?
Yes, sir.
Okay. So moving forward, so let me clear this. Let me again share this screen. Okay, so now we'll talk about this hypergeometric. Okay, so hypergeometric, as I mentioned, you need to know the population size and the number of successes in the population, and the sample size and the number of successes in the sample. Okay, so let's take this example. A poker uh, hand consists of 5 cards dealt at random. So the poker is taking 5 cards and he's randomly, okay, he's selecting from the 52 cards. Okay, so here the sample size is 5 cards. Okay, and the total population is 52 cards, of which 626 are red, and we know that. Okay, in 52 cards, 26 are red. Okay, so this information everyone knows about it. Okay, and the rest are black. Now the poker hand is dealt. Find the chance that the hand contains 3 red cards. So he is drawing 5 cards at a time. So sample is 5. So now I want to find out the probability that what is the chance that I will get 3 red cards out of those 5. So here the total population is 52. The number of red cards in the population is 26. The sample size is 5. And I am interested, to find out the probability of getting 3 red cards, which is x equal to 3. So here, so I'll take this hypergeom. Okay, hypergeom, here, this is again from stats. And in hypergeom, I'm going with the CDF. So this is a sequence at which you have to pass the parameters. First, you have to pass x, which is 3, then m, which is your population size, which is 52, n is the number of successes in your population, which is 26, and this is your sample size 5. Okay, if you pass this, it will give you the probability of getting 4, how many? 3 red cards, or less than 3, less than 3. Okay, so this is the overall probability of getting 3 or less than 3. So this should be what is the chance of getting at most 3 red cards. Okay, then we can use this CDF function.
So it is clearly saying contains 3 red cards. So is it not exact value like that PMF?
Once again, this PMF should work here.
I mean, you said that
Yeah.
cumulative is the range. So here it is clearly saying contains 3 red cards. We want 3 cards. That's what I'm saying.
Yes. So for exactly 3 red cards, it is PMF. Okay. So it is saying 33%. If you want to find out 3 or less than 3, then you go with this CDF. That is saying 82% or 83%. Got it?
Got it, sir.
And similarly for exponential. Okay. So for exponential, we require 2 parameters. Okay, and those 2 parameters you should pass here, and then you can find out the probability of having that particular value or less than that particular value. So basically, for continuous variables, we generally use CDF. We don't go with PMF kind of function for exactly that particular value. So whenever we are dealing with continuous variable, we generally want to find out what is the probability that I may get a value somewhere in that particular range. Okay, if the temperature. So we don't, in the business terms I'm talking, nobody would be interested to know that what is the probability that I will get a temperature of 10.5 degrees Celsius or 10.56 degrees Celsius, right? So mostly the interest would be what is the probability that a temperature either may go above this particular value or below this particular value or may stay in this particular range. So that would be the interest. So that's the reason we go with this CDF function only for continuous variables. Okay, so I'll share this code, guys. Okay, so go through it. Okay, try to understand every distribution in detail and see that how this PMF, CDF functions are working or this PPF functions are working. Try to take different scenarios and play with that. Okay, so that you will able to understand how that function works. Okay, and how you have to use those parameters in those functions. All right. So that's about probability and probability distributions, guys. I hope you got a good understanding about the way these probability and probability distribution works, and their application in solving some of the problems, business problems. So it's all about, guys, understanding or getting some idea about a particular event occurrence, okay, and the likelihood of that particular event to occur. And if we get some understanding or some idea about that particular event's occurrence, then based on that, we can take a better decision. So it's all about how we can bring out the insights to the business so that they can take a better decisions. Okay. And after this, we'll talk about hypothesis testing. So from tomorrow, we'll discuss about hypothesis testing, and that is primarily comes under inferential analytics. So we will understand how with sample, we can refer something about population and what kind of tests we can do, to infer something related to the population with the help of sample. So that we will discuss from tomorrow. And there is a relationship, guys. Whatever we are discussing now, there would be a relation with some advanced concepts in machine learning. So here I'm just building a base now. So these are all fundamentals. So for these small topics, I'm giving you certain small examples. But later, as I mentioned, once we understand the other advanced concepts, so we'll understand the bigger picture. Okay. So even the problem statement, as I mentioned, business problems can be solved through multiple solutions. Okay. And overall, you need to understand, yes, overall, you need to understand what kind of techniques are possible, what kind of techniques you can use, to come up with a holistic solution to your business. Okay. So we are going step by step, we are building a base and which will help us, to reach to that advanced level. All right. Then we are good. And again, this is not a complete exhaustive uh, coverage of these topics. As I mentioned in distributions, probability distribution, in statistics, there are several other distributions also. But I picked up the most frequently and most special popular distributions which we generally use more often. Okay. But again, these are not limited to only these distributions. There are many other distributions also. Okay, but we are understanding the concepts, and based on these concepts, okay, we can able to step forward and we can able to understand the advanced concepts. So I'll take a pause here. Let me know if you have any questions. Are we good? Okay. All right then. And thank you guys. We will connect tomorrow. Have a nice day. Bye bye.